All right, welcome back. Today we have kind of a lot to cover, so we want to make sure that we are really tuning in. Write down any questions that you have, and then make sure you reach out with those questions after you're done going through the notes if things aren't cleared up by the end. So today what we're going to talk about is how we can use similar figures and how they use proportional reasoning to help us, kind of like we've been doing in the past, figure out unknown quantities. Now, when we talk about similar figures, we're talking about shapes that look like these two triangles. And what you're going to notice about them is that similar figures, right, are going to have the same shape, but different sizes. So it's almost like you shrunk or enlarged them. So they're going to look the same, like shape-wise, but they're either bigger or smaller. With those, you're going to see kind of these little tick marks in the corner, not tick marks, but kind of these arc marks. So if you notice here for angle A and angle D, they both have 1, angle B and E each have 2, and angle C and F each have 3. These are what are called corresponding angles, and these arc marks show that those corresponding angles are the same. So angle D is exactly the same as angle A, E is the same as B, and C is the same as F. So their corresponding angles are congruent. And when we say the word congruent, what that really means is that they are equal in measure. Now, their angles are exactly the same measure, but our corresponding sides are not the same length, but they are proportional. And as we've talked about before, like when we were doing scale and things like that, you'll notice that they maintain the same relationship. So just to review, similar figures. They are shapes that look the same, or they're shapes that have the same shape. That's really redundant, I'm sorry. But different sizes. They maintain proportional relationships. For their sides. And they often look, it's often achieved by enlarging or shrinking the item. When we talk about similar figures, what we often talk about is their scale factors. So that is how much they are in relationship to each other. So it's formed by a ratio of corresponding sides, but what you want to think about is what one figure is multiplied by to get the other. So for example, is it doubled? Is it cut in half? Is it 2/3 as large, right? So that's the scale factor. So what we're applying to one of the shapes to get to the other. So sometimes, right, for example, you can double a shape, and then if you went back the other way, you would cut it in half. So depending on, so scale factor is always determined by the what the new one looks like compared to the original. So depending on the order can change the scale factor. All right, and we use similar figures, right, in the grand scheme of things, a lot of times in things like indirect measure, where we're going to use properties of similar triangles to find measurements that would be difficult to measure directly. So for example, right, it would be really difficult to measure the exact height of a tree, because even if you could climb up, it would be really difficult to get the ruler, right, to go all the way down to the bottom. And so we can use indirect measure, and that's often through the use of shadows. To find the measurements of those types of things like trees and stuff like that. All right, so in order to figure out our scale factor, right, or just to use indirect measure, right, the big thing is you always want to find the matching or corresponding sides, and then you're going to set up your proportion based on that. So we could do small side to big side is small side to big side. You could do small triangle, or like the smaller shape to the bigger shape, things like that. So there is some flexibility as long as you are keeping things the same when you set it up. When you start flipping things around, that's when our proportion gets tricky. So we'll look through a few examples. So let's start with just identifying scale factors. So how is it changing from one shape to the other? So we're going to look at, say we have quadrilateral A, and we're scaling it to create quadrilateral B. So it's like I have a copy machine. So what would I have to do to A to either shrink or enlarge it to get quadrilateral B? So what we're going to do, I'm going to draw a little picture over here. And this one's going to be quadrilateral A. I just drew it as a rectangle. And we know that quadrilateral A has a side that is 8 centimeters. So I'm just going to make that one right here. And we have quadrilateral B is a corresponding side of 12. So I know it's going to be an enlargement because B and 12 is bigger than 8. And because we know it's a corresponding side, since I put the 8 right here, its corresponding side would be over here. Now, since it's a rectangle, officially I could put it on either side. But to keep it the same, I'm going to put it in the same spot. So we have identified our corresponding sides. And we're going to set up the ratio because we're changing from A to B. We want to figure out how we got to B from A. So in our ratio, B is going to come first. So in this case, our ratio is going to be 12 to 8 because that's our ratio of B to A. We want to simplify that. 12 and 8 can both be divided by 4, which would give us a ratio of 3 to 2. I'm going to go ahead and change it to a decimal. And so in this case, our decimal would be 1.5. So our scale factor from A to B is 1.5, meaning we had to take our dimensions from A, multiply them by 1.5, and that's how we got our dimensions for B. So B is 1.5 times bigger than figure A. So what does that mean? So here, what we can do is if we know a different side of A is 10 centimeters, so now we know that this side is 10 centimeters, we can use that scale factor to find the corresponding side in B. Since we know that 8 times 1.5 is 12, I can take 10, multiply it by that scale factor of 1.5, which is 15. And so then we would know that the side length of that other side on B would be 15 centimeters. And we can even check that by setting up a proportion. So for example, I'm looking at 8 compared to 12 because those are our corresponding sides, has to be the same as 10 to x. Going back, using our cross products, that means 8x has to equal 12 times 10. And actually in this case, we're testing out to see, so I'm not going to use 15. Oops. I'm actually going to go ahead, or not going to use x, I'm actually going to use the 15 there. So instead of 8x, I'm going to have 8 times 15 just to see if it's proportional. And 8 times 15 ends up being 120. 12 times 10 is 120. So we can see that it maintains that proportional relationship. But we just did it instead of using the proportion, we used the scale factor. All right, so that was a lot. So let's kind of keep going. So let's just look at, oops, actually looking at shapes with similar figures. So here we have two right triangles. We want to find the value of x because we know that these triangles are similar. So here, what I'm going to do is I'm going to identify that right angle. So in this case, it's right here. And then we can kind of see the two legs of a right angle and then what's called the hypotenuse. So I know that x corresponds with 5. So part of my proportion is I know that 5 is going to be compared to x. Now I have some freedom. I can pick any of my other two sides as long as I pick the corresponding sides. So I could either do 4 and 8 or I can do 3 and 6. It does not matter. I'm going to go ahead and use 3 and 6. Since I used my smaller triangle on top, it's going to be a smaller triangle on top to our bigger triangle on the bottom. Once again, we can use those cross products. So I'm going to do 5 and 6. And then we're going to do 3 and x. So 5 times 6 has to equal 3x. And we can see that x would equal 10, meaning that our missing side on our triangle would be 10 units. All right, so why don't you go ahead and pause the video. I want you to try example 2 on your own and then see how you do. All right, so a small rectangle we know is 4 inches wide by 6 inches long compared to a larger rectangle that is 12 inches wide, and we want to know how long it is. So in this case, I'm going to change up the proportion just to show you that you can do it in different ways. We could do like we did before where we did small to large, but what I'm going to do this time is I'm going to set up my proportion as smaller triangle to smaller triangle, but I'm going to do width to length has to equal width to length on our larger triangle. So as you can see, I can set up my proportion in different ways as long as I keep it consistent. Now, different ways that we can do this. We could use scale factor. We could use a bunch of different things. So in this case, I'm going to try scale factor because I see that this works out really nicely. I can see that this one is times 3. So that means on the bottom, we would also multiply by 3. So x is going to equal 18 for that missing side, or 18 inches. You could have also done cross products. It would still work the same way, and you would end up with the same answer. All right, now just looking at an example that uses indirect measurement like we were talking about before. So this is kind of more that real life application of when we use similar figures. So we know we have a flagpole, but we don't know how tall it is. So here's my flagpole. We don't know its height, but we know it casts a shadow that's 20 feet long. And then I have a person standing near the flagpole, and we know that this person is 5 feet tall, and their shadow is 4 feet. So we're going to go ahead and set up a proportion. Once again, we could do person to shadow, shadow to person, however we want to do it as long as it's consistent. So I'm going to do shadow to person. So I'm going to start with what we know. So we know the person's shadow is 4 feet to a 5-foot person. We know the flagpole shadow is 20 feet, but we do not know how tall our flagpole is. So once again, we can use cross products, we could use scale factor, whatever kind of works best for you. Once again, these numbers are really nice, so I'm just going to go ahead and make this easy and use that scale factor, and I know that it's times 5. So here, because 4 times 5 is 20, 5 times 5 is 25. So the height of our flagpole would be 25 feet. If you did cross products, right, it would have just been 5 times 20, which is 100, is equal to 4x. And if we do 100 divided by 4, also 25. All right, looking at one more thing, just looking at scale drawings once again. We're going to set up our proportion. We know our scale is 1 inch is equal to 5 miles. And we want to know if the map, oops, that's not the scale we're using. On our map, it's saying that 1 centimeter is 10 kilometers in real life. The two cities are 4.5 centimeters on the map. We want to know how far apart they are in real life. So this time, just to review, I'm going to use cross products. So we have 1x is equal to 10 times 4.5. So 1 times x is, oops, is just x. Has to equal 4.5 times 10, which is 45. So in this case, it's 45 kilometers that they are apart in real life. So go ahead and read up those common mistakes. Otherwise, reach out if you have any questions. I know this was a ton today, but really just building off of what we've been doing and just looking at it in a different context.